Hola. Good afternoon, everyone. Thanks for coming in. Welcome to the session, Back to Indexes, the Original Culprit. I presented this session last year at TechEd North America. It was very well appreciated. And thanks to Microsoft, I get this opportunity again to present this session at TechEd Europe. So it's indeed an honor and privilege to be presenting this in front of you. That's my representation of big data. And that's big data with compression. So you really do not need big hardware to have big data. You can run on small hardware. But most importantly, on a serious note, back in India, I worked for E-Dominer Systems and People Were India. And we worked for some very big SQL Server customers, more than 120 SQL Server customers. And majority of the assignments that we do are related to troubleshooting and performance tuning. And in most of those assignments, when we go to the customer sites and work with their large databases, majority of the cases we find that there are issues related with indexes. The right indexes are not there. There are redundant and duplicate indexes. In a nutshell, overall, the indexing strategy is not very well defined, probably because there is less understanding amongst the DBAs and devs that work with our customers. So what I have done is taken many of those real-world scenarios and real-world examples, converted them to some academic versions here, and I'm going to present those scenarios to you. So these are some real-world cases that we see with these large customers, and that's what I'm going to talk about. Yes? Okay. And yes, of course, I will also have to justify the title of my presentation, which is, Why Am I Calling Indexes as Culprits? So this is what is going to be your takeaways kind of agenda. It's a demo-heavy session. I precisely will present 3 demos to you, 3 indexing scenarios. The first one will be related to missing indexes feature in SQL Server. And I assume that all of you know about missing indexes feature and the missing indexes DMVs. So I'm not going to introduce the feature to you, but I'm just going to show you certain caveats with this feature. We will then move on to left-based subset mechanism. Is it so easy to define the order of columns when you're designing indexes? Moving forward, we are also going to talk about the database tuning advisor. And again, I'm not going to introduce the tool to you. I assume all of you will know what the tool is. But I'm again going to show you certain interesting cases when it comes to DTA. And that demo is related to another demo related to multi-column indexing. And that's slightly put as a suspense because I will involve you in the demo, and I'm going to ask you certain questions. Overall, the takeaway for you will be, in a nutshell, your indexing strategy and how does the optimizer choose the right index given a particular database and given a particular workload. By the way, this is a very challenging time slot. I come between you and your lunch. So, if I extend, you are going to give me very bad scores. So without further delay, let's begin with the first one. Demo number 1, which is mistake number 1, missing indexes feature. So I have a database here called lob, and this database lob is is just a representation of any line of business database. It has certain tables like customers, employees, orders, and shippers. The one that we are going to work with is TBL orders. This table, TBL orders, has 1 million rows. Okay, so if I just do a select count star from TBL orders, you would see we have about 1 million rows on this particular object. I'll also show you that we, as of now, do not have any indexes, nor do we have any statistics on this table. So this table is a heap. This is one of the workloads that needs to be tuned. Look at this workload. We are joining three tables, that is TBL orders, TBL customers, and TBL employees, on certain columns that are common amongst these tables. Most importantly, we have to focus on the predicate here. The filter is on order ID, which is one of the columns of TBL orders, right? And the predicate says that the order ID has to be greater than 1 and less than 1,000. And remember, this particular table has 1 million rows. So this query, as you can understand, is highly selective. It's going to return you low number of records, approximately 1,000 records. When I run this particular query, and I will include the actual execution plan, and I go to the execution plan, I get a missing index hint here. And this is something that all of you know, right, from SQL Server 2005 days. In the execution plan in SSMS window, if you do not have an index that the optimizer thinks you should have, which will improve the performance of your query, it is going to recommend this to you. Now, what I want to do is actually look into the recommendation. So I will right-click and go into the missing index details. When I look into the missing index details, apart from the name of the index, the most important thing to be observed here is you have the index is recommended on order ID column, right? So that is going to be the indexing key. The other column goes into include. So our focus here is on order ID column. So my question to you, are all of you in agreement with this suggestion? Yeah? It's a non-clustered index. It's trying to be a covering index, covering the entire query per se. So because your predicate is only on order ID, and you want to seek on order ID is chosen as the indexing key for the index. Rest of the columns are moved into included. The focus here is not the included, the columns that go into the included keyword. The focus here is on the choice of index key. Okay, in case you still want to decide, let me quickly go and create this index. I'm going to name this index as TBL. Okay, sorry. Let me put this as IDX TBL orders underscore order ID. And just so that we can identify it well, I put it 1 underscore. That's too small. So here is what I give the name as of the index. Okay. I prefix it 1 because we will create multiple indexes, and then it will be easy for us to identify which index the optimizer is choosing. Click on OK, and I will go and create this index. It's just going to take about 4 or 5 seconds because we have 1 million rows. On the lob object. So yeah, any feedback? Do you think this is an appropriate index for the optimizer? No? Okay. Come on, SQL Server, don't embarrass me. This is TechEd. Okay, done. I will run, so the index is in place. Let's go and run this. And by the way, did you observe when we ran it last time, because it was a heap, we actually did a table. The optimizer did a table scan, right? Very easily understandable. Let's go and execute this once again. You get about 998 records, which is close to 1,000 based on our filter. And if we go to the execution plan, and this time, the index is rightly being used. Right? No disagreements. Because this was the choice of the optimizer that you need to have an index where order ID is the indexing column so that you can seek on that particular column to fetch the matching rows. However, here is the interesting scenario. Suppose we change the predicate value from 1,000 to 10,000. Now you want approximately 10,000 rows out of 1 million rows, right? And do you also notice that when we ran this query, there is no hint anymore. There are no hints because we created the right index that the optimizer wanted. I will go and create this. I will run this query once again, now with slightly changing the parameter value out there. And I go into the execution plan. There you go. This time, the optimizer suggests me to create another index. So I already have one index on order ID. It tells me to create another index. Now let's see what that recommendation is. Go to the missing index details. This is what I get. This time it tells me to create an index, and it tells me to include employee ID also as part of the index key formation. So this is a multi-column index. It's a composite index, and my index is going to be based on employee ID and order ID. Now, I really don't know why is the optimizer suggesting me to create this index. Okay, we will figure that out. But let's go and create this index. Let's just do what our optimizer tells us to do. So I will create this TBL IDX underscore TBL orders underscore EMP ID underscore order ID. And just so that we can easily identify it, I'll prefix it with 2 underscore so that you know this is the second index. That's the name of the index. We'll go and run this. Remember, in the previous index that we created, employee ID was actually included as part of the included list. And now for the second recommendation, it has been taken up from the included list, and it has been recommended to be put into the composite index key formation here. So just let's give it a few seconds again. So I will close this one because we are done with this. Come on. So this is done. I will run this query once again. Now, how many of you believe that optimizer with the same set of parameter values, same constants, same literal values, it's actually going to choose the second index? Show of hands. Second index. Now, you're already getting the hint that it won't use it. Okay, so anyway, let's go and run this. We go to the execution plan. No more hints, but did the optimizer use the second index? No, it did not. Then why did it recommend it? So we'll figure that out in a while. So let's go back. So in one of my previous conferences, it was said that because a plan already exists in the plan cache, the optimizer is taking that same plan again, but that is not the case. Even if I run dbcc free proc cache, mind you, you shouldn't run these statements in your production environment. This is just for trial and demo purposes. And now there is no plan in the plan cache, and if I run this again, and I go to the execution plan, the optimizer still resorts to the first index. It doesn't need the second index. Okay? So, I'm sure all of us are curious to know as to why exactly did the optimizer suggest the second index. Now, for me to demonstrate that, let me actually drop both the indexes. I'll drop both the indexes, and this time I will run this query with the same parameter value 10,000. And look at the interesting aspect here. I go to the execution plan. It suggests me an index, rightly so. I will right-click, go to the missing index, and this is the one that we got in the first place, right? But whether this is good or bad, but this is how SSMS is. If you go into the properties window, you will actually see in the missing index hint, column group, you can actually figure out that the optimizer is actually suggesting you 2 indexes. The optimizer is actually suggesting you 2 indexes, the one with order ID and the second one with employee ID and order ID. Now, here is the story. The story is, when you ran the query first time with parameter values 1 and 1000, it only recommends you order ID, index with order ID. But when you run this query with parameter value 1 and 10,000, it recommends you both the indexes. It recommends you both the indexes. The SSMS tooltip here only shows you the detail of the first index, or the index that it thinks is more important or will have greater impact on performance than the other one. All right? Which means if I go and create this index and I run this query again, it's going to recommend me the second index. So what really is the lesson for us here? Okay? Please do not follow the recommendations blindly. That's one of the first lessons to be learned when it comes to missing indexes feature. Do not follow these recommendations blindly. Review them before you implement. The point that I'm trying to convey, the message that I'm trying to convey is, for that given query, the optimizer is actually never going to use that second index. But if we are less knowledgeable about indexes or the optimizer, and that's what we see with our customers, majority of the DBAs and devs will actually land up creating the second index. Now, what really just happened here was you landed up creating a redundant index. So think about it. If having one index per query is bad, having two indexes to satisfy one workload is even worse, because that's going to have detrimental effect on the performance of your update and modification queries. So keep an eye, and if we go back to the query workload once again, and let me quickly go and create both the indexes. So we'll just go and specify one underscore IDX. That's the first one. I want to actually now prove a simple point here. Why did the optimizer actually recommend the other index? Is because of this. So now you see the parameter value is same. It recommends me the second index. And I go to the missing index details. We'll go and specify the second one. dx underscore tbl orders mp id underscore order id. So now I'm back with both the indexes. And let's see. If we run this particular query, whether it's with value 10,000 or we run it with say like 20,000 or any number of parameters and any number of times we run it, keep an eye on the unused indexes. Because the second index recommended by the optimizer is not used at all, here is a small script that you can actually write to find out that the second index is nowhere on the list. It's not being used at all. It's only the first one that is being used, and you can see it has been used 5 times for seeking, and that's the index ID, etc. So that's how we have used it. And the performance difference is also pretty evident if I compare the table scan versus the first index. Let the optimizer choose what it wants. You can clearly see that there is a difference of 96% versus 4%. So that's a huge performance difference between table scan and the first index. But if I compare the performance difference between the first index and the second index, so I put a hint here, forcing the optimizer to use the second index, and when I compare their performance, you can clearly see a performance difference of 27% versus 73%, which means if the optimizer was actually using the second index, it would have been a lot more expensive from a query, from the efficiency of the plan perspective. But one question is still not answered, which is why the hell did optimizer recommend the second index, right? That question is still not answered. It's because of so I need to go a bit deep into the internals of the optimizer. That's not my focus for the session, but just to let you know, optimizer is a cost-based optimizer. I'm sure you know about this. You have read it a number of times. It evaluates multiple candidate plans before it comes up with an efficient plan. So depending on the code path that the optimizer takes, it finds that both the indexes are appropriate or could improve performance. That's the reason why it recommends you both the indexes. Because the queries with parameter values of 1,000, 10,000, 20,000 are still highly selective, which means it is going to return you low number of records. But suppose you run this query, where you see the range I've put as like 1 million or so, which means this query is going to be low selective. It's going to return high number of records. In such case, the optimizer will actually, okay, so I'm not going to run this because it's going to return a huge number of records. I'll go and just run the estimated execution plan, and I will show you in such case the optimizer is actually going to use the second index. Right? So, well, with this, the summary doesn't really change. It still remains the same. What just happened was you created a redundant index unless you have variety of selectivity. But given the fact that you're never probably going to get all the records from a table, you will have parameter values. And if you know that the selectivity is going to be very high, which means you're returning low number of records, it's only the first index that's going to be used. These are some interesting cases that we see with customers, and I've created some examples out of it to showcase that to you. Yes, sir. Okay, it used the second index is because if you see there is the join is on actually employee ID. So it actually uses that index both for filtering purposes as well as for joining. That's why you have a composite index on employee ID and order ID. And because it's going to return a huge number of records, it finds that index to be more cost effective than the first one. So that's how the optimizer is. But as I said, you probably will not have 2 indexes or 3 indexes or 4 indexes just for one workload. That's going to be a disaster, right? Another question? The gentleman there, okay. All right. So the idea here is missing index feature. Great feature, good feature, but please use it with review. Use your own judgment. Just don't follow the recommendations blindly. That's my first demo. Okay. Demo number 2, which is mistake number 2, left-based subset. This is a demo-heavy session, so I'll have less of bullet points on the PowerPoint, but more to show you. Okay, so I will just close this and open up the second one. Oops, this is so big. All right, so we have this database, AdventureWorks 2012, very popular database. I will use this, and I will make a copy of person.person table as person copy, just to demonstrate this example. This table, person.copy, has a number of columns that I'm going to play with, like business entity ID, person type, first name, middle name, last name, email promotion, etc. Just to be sure, we don't have any statistics and we do not have any indexes on this object. It's a heap, just like my previous case. And here is a small query for you. So there are 3 queries here, okay? I want to give you 30 seconds for you to give me some answers as to what indexes would you really design to satisfy these 3 workloads. All right? Query 1 gets data from some columns, but most important thing for you to observe is the predicates. So we have a predicate on first name and last name. The second query has a predicate on email promotion and person type, and the third workload has a predicate on person type, first name, last name. Because we do not have the liberty of time to really go and discuss a lot of options, I'll tell you, don't focus on the select list. Okay? Ignore the select list. Focus on the predicates. The first query, first name, last name. Second one, email promotion and person type. And the third one has person type, first name, and last name. Take 30 seconds. Think about it. Do you want to have just 1 index, 2 indexes, or 1 index per query, which means 3 indexes? Just give it a thought. Meanwhile, I can have some water. Okay? Any answers? Yes?
I would probably put an composite index on first and last name, and then a second index on person type.
Okay, 1 index on first name and last name, and the second index on person type. So I have a recommendation, okay, 2 indexes, one on first name, last name, the other one on person type. Any more recommendations? Yes, sir? You want to have 2 indexes? Just one, on last name and person type? Okay. 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 So, well, that's a fair, valid point that you need to know the distribution of data. But I would humbly disagree for the moment, because you want to seek on these columns, true or false, right? So whether this particular column has, variety of selectivity or just the density is 0, you can still seek on this column. So depending on what number of person types you have, you can still have that column as part of your index key formation. All right? Yes. That's your first index. Okay. 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 So let's. Won't be possible for me to type out all the recommendations. Okay. But here is what you could do. You can have an index on first name, last name, person type, and email promotion, and another index on email promotion, first name, last name, and person type. Okay. Now, all the recommendations that I have got from you, just keep that on hold. And the concept that I'm trying to explain here, you will apply that concept. You will apply your indexes to that concept. Suppose I go and create the first index. Okay, first name, last name, person type, and email promotion. Okay, and let's go and include actual execution plan to see if the index is being used. And I run the first query. Is our index being used? Yeah. So the index that we created is being used. Why? Because first name and last name, these 2 columns are actually being covered in our index. So you are able to seek on that index. What about the second query? Will you be able to seek email promotion and person type? It is actually being part of our index key formation. So if I run the second query, I will see the index is being used, but only for scanning. The optimizer is actually not seeking on the index. Now, these are certain things that we have seen with our customers. The question is, why hasn't the optimizer actually seeked on that index? Is because you are filtering in this particular query. The filter is on email promotion and person type, but email promotion and person type, neither of these columns are the first or second columns of your index key formation. So the way how the data is laid down in the B tree structure is first name, last name, person type, and then email promotion. So you actually cannot seek. If you want to seek on an index, it has to follow a left-based subset mechanism. It has to follow a left-based subset mechanism, and I will reassert this point in a moment. But let's go and look into the third one. The third one is person type, first name, and last name. Your answer, will it be able to seek on the third one? So when you run this, look at this. The filter is on person type, first name, and last name. First name, last name, person type. Are 3 columns being covered here? But is the order same? Is the order same? The order is not same, but the order of your predicates in your where clause is irrelevant. It doesn't really matter in which order you put the predicates in the where clause. What is more important is, if you are trying to filter on these 3 columns, are these 3 columns covered here in any order? They are. And left-based subset, which means I have first name, last name, and person type. Irrespective of the order, all the 3 columns are being covered, are being used in my predicate. So this particular query will definitely seek on index 1. Now, the scenario here is, I have my second query, which was actually was not able to seek on that particular index. So what can I really do? I can have a second index because I want to seek on email promotion. I want to seek on email promotion in my second query. I can create a second index where I can put email promotion as the first column, followed by first name, last name, and person type. And I will tell you upfront that this is not the right index, but I'm creating this index just to prove my point on left-based subset. And this is the most common mistake I see with our customers, which is as follows. I'll go and create this index. There's no point in running the first and the third query because you know that an index already exists for them. We have to focus on the second. If I run the second query, and now I have an index which starts with email promotion, is it seeking on the second index? It does. But the point is it a full seek or is it a partial seek? Now here is a concept of fully seekable and partially seekable. What really has happened here is, yes, this index 2, is being used by the optimizer to seek on email promotion, but unfortunately, it is only seeking on email promotion. It is not seeking on person type. The reason why it is not seeking on person type is in your index, email promotion is the first column, but person type is not the second column. If you want to seek on all the columns, it has to follow left-based subset filtering mechanism. But how can I prove that it's actually not seeking on person type? Here it is. So my second index, I will run this again, second query, and I go to execution plan. And I'll take my cursor over the seek here and look at this on the tooltip. Look, observe the, oops, sorry, that's zooming too much. Okay. Look at the seek predicates, and you can see we are seeking on email promotion, right? But you, in the seek predicate, do you see person type? You can't see person type. Person type actually goes into something what is called as residual predicate. So you are actually not seeking on person type, you're scanning person type. So the way the data is laid down on index 2 is email promotion, followed by first name, last name, and person type. So it seeks on email promotion, and from that point, it scans the data. So it is partially seekable. It is not fully seekable. In order for us to let the optimizer fully seek, we could actually create these two indexes. So let me drop these ones. We could actually create one index on first name, last name, and person type, and the second one on email promotion and person type. Now, this is your choice here. This is your choice. It's not compulsory that you have to follow these two indexes. You could choose other combination that could perform better. But the point that I'm trying to make here is I have 3 workloads and I have 2 queries that are going to fully cover the workload. Sometimes you might have to be satisfied with just partial seeking because, as I said, you can't have one index per query, right? That will be a lot of non-clustered indexes in your databases, and it's going to have really bad performance on your update, and your modification DML queries. But these two indexes, if I create, so the first one, index ID, first name, last name, and person type, and the other one on email promotion and person type. So the first one is actually going to, the first one will cover, the first index is going to cover query 1 and query 3, right? Because all the 3 columns, so if you see the first query, it has first name and last name, and our index has first name, last name, and person type. And the third query has first name, last name, and person type, which are all the 3 columns in the index. And query 2 will be covered by the second index, which has our columns in same order, email promotion and person type. So what are the lessons for us here? Are these. Understanding the index key column order, that is very, very critical. As I said, these are common mistakes that I see because the execution plan shows that you're actually seeking, but you're not fully seeking. This is where looking at the tooltip is important. If you look at the tooltip, you can see on which predicate are you able to seek, and on which predicate it is goes as a residual predicate on which you're not able to seek. So, and let me tell you, friends, the index key column order is very, very critical, because it's, look at this just one small example. You know, we got to discuss so much with this one small example. So it sometimes seems easy to design an index and put just all the columns that you get in the predicate, but it's not as trivial as it seems to be. It really requires a bit of consideration, trial error, to understand what should be the order of columns. But this is where all the performance is. In a multi-column index, especially in a multi-column index, when you have too many columns in the index key formation 2, 3, 4, the order is very critical, because you might have number of workloads that are actually running on the same table with different columns, different predicate values. So it's not that trivial. The lesson here is, so the query filter happens, where's my mouse? Yeah. The query filter happens using a left-based subset mechanism, which means an index is fully seekable by a query if all the predicate columns of the query are also index columns in a left-ordered fashion, starting with the first column. So that's the idea that I showed about first name, last name, person type. That is the left-based subset mechanism. There is one exception, though, which I'm going to talk about in the next example. Yes. Highly selective, low selective? Yes, absolutely. It's a common guideline. It's a common recommendation to put the most selective column as the first column in your index key formation. Okay? And in fact, that's a great question, by the way, because my next demo is actually talking about that. Okay? So, great one out there. Friends, are you enjoying the session? Yes. Yeah? Okay. Is my English okay? You can understand it? Okay, gracia. Okay, so demo number 3, which is mistake number 3, what we see with customers. And I'm not going to give you any hints here, so that's why I put it as suspense, because I want to involve you again and ask you a few questions around. So here is my demo number 3. So there's a table here in AdventureWorks, which is contact 2. Oops, I guess the mouse is contact. There's a table called contact, and what I do is, just for the purpose of this demo, we'll create a duplicate of contact as contact 2, and then we will create a clustered index on contact ID. I repeat, we have a table called contact. I will create a duplicate as contact 2, and we will create a clustered index on contact ID. And this is the workload that I want to give to all of you. You tell me what should be the index that you want to create to satisfy or to improve the performance of this workload. Before you give me your answer, there are certain things that you should observe. This workload has 3 predicates: first name, email promotion, and contact ID. And all of you know that we already have a clustered index on contact ID. So you're only left with email promotion and first name. I'm just trying to make it a little easier for you. This table has a total of 19,972 records. If you run this workload, you're going to get 77 records. And selectivity, the point the gentleman was trying to make here, the selectivity. If I run this workload only with first name, like L%, only with this predicate, I'm going to get 872 records, which is approximately 4.3% selectivity of the entire table. If I run this workload only with email promotion equals to 1, I'll get 25% of the table being returned. Okay? And if I run this workload only with contact ID, so contact ID, so you know less than 10,000, which is, we have total 19,000 odd records, so we get 50% of the table. That's the selectivity factor of these 3 columns. Design an index for this workload. There could be a lot of options here, but It's relatively easy because we already have a clustered index on contact ID. And I'm sure all of you know that every non-clustered index contains the clustering key value. True or false? Yeah. Every non-clustered index contains, by default, contains the clustering key value because of the pointer. So you're only left with email promotion and first name. Which means if you actually create an index, a non-clustered index, on email promotion and first name, it's going to cover this entire workload. True or false? Yeah, it's going to be a covering index because contact ID is automatically included, and those are the other two columns, first name and email promotion. So do you really want me to show you and run these queries with only 1, 2, and the third predicate? I think that's understandable, right? So let's come to the point. The easy part here is we really can drill down only to two options, what you see at the bottom of the screen, option 1 and option 2. And the only difference between these two options is the order of columns. It's just swapping. So the first index has composite 4. The first index has column order as first name and last name. And the second index has column order as email promotion and first name. You create either of the index. I'm sure you don't want to create both the indexes. You create either of the index. It's going to be a covering index, right? But the question is, which index do you create? You know the selectivity factor, right? First name is highly selective, followed by email promotion, followed by contact ID. That's the order of selectivity. Before you give me your answer, let's go and ask Database Tuning Advisor. How many of you use Database Tuning Advisor? Okay, many of you, great. So let's go and ask DTA about this. So I'll close this and open my third one, query to be indexed. Okay, we'll use AdventureWorks. I'll drop this table in case I have it. It's okay, I don't have it. Let me make a copy as contact 2. We'll create, as I said, we'll create a clustered index on contact ID. And this is the query that we want to tune, right? So what I've done is I have created a file called dta.sql, and I've actually just put this query here. I'm sorry for the font size. We will put this workload as an input to Database Tuning Advisor. So let me go and start DTA program, SQL Server 2012. Where is DTA? Performance Tools, Database Tuning Advisor. By the way, what do you think, composite 4 or composite 5? First name, email promotion, or email promotion, first name? First name, email promotion, composite 4, because of the selectivity factor? Okay. Interesting. Interesting. Let's see what DTA says. Okay, so where is our file? That's in C drive. In my demo, dta.sql, I will take AdventureWorks for the database to be tuned, and for workload analysis, AdventureWorks. And I'll click on Start Analysis. DTA is a good tool. It's a much better tool over what we had, like index tuning wizard in the early days. I think SQL Server 7.0 and SQL Server 2000. So we get some recommendations here, and what I am going to do is, friends, so there's a recommendation on statistics, and there is a recommendation on index. So we'll ignore the statistics for the moment, and we'll just look into the recommendation on the index. Okay, so I can zoom in here. I don't need to copy. This is the recommendation that DTA says. Now, for a moment, you can forget about contact ID. You can ignore contact ID because DTA creates hypothetical indexes, and it is not taking into the consideration the fact that you already have a clustered index on contact ID. So contact ID can be ignored out of the equation. Otherwise, then what you get is first name followed by email promotion. That's the recommendation. which means composite 4 is what is recommended by DTA. Okay? Yeah, any? Okay, yep. So let's actually open up both the indexes. So we go to the indexing options. So there are tons of these indexing options that you can actually, I mean, this is what we do day in, day out, right? Create different indexes, combinations, but we don't need to look into so many of them. We can just focus on composite 4 and composite 5. Let's do one thing. Let's go and create composite 4. I'm sure the optimizer is going to use this index. There's no doubt about it. As I said, both the indexes are covering indexes. But this is what the DTA recommends. Let's also go and create the second one. It doesn't do us any harm. We can check which one the optimizer uses. So I'll create the second one also. Go back, climax time. We turn on the actual execution plan, and we look into what has the optimizer done. It does not take composite 4 as recommended by the DTA. It takes composite 5. It prefers the index with email promotion followed by first name. Now this is another common mistake that we see with our customers. You know, when we work with DBAs and devs on our customer side, and we look at their databases, their workloads, and we see these as common mistakes. And I've created a small example out of this. So the question here is, why is the optimizer actually preferring composite 5 over composite 4? The first thing that I want to do here is actually check the performance difference. Is there really a performance difference between composite 4 and composite 5, right? That's the first thing I will check. So what I can do is use the hint, because I know the optimizer, when I run the query, it is using composite 5. I give a hint of composite 4, and I run both of them to see the performance. And I can clearly see that there is a performance difference of 65% versus 35%. That's a lot, isn't it? That's a lot. Which means if the optimizer only had composite 4, that would have been like doubly expensive than composite 5. And the another important aspect here is, if suppose, let me go and drop both these indexes just for a moment. And just let me create only composite 4. I'm doing this because this was another question asked by one of the gentlemen in my previous previous conference, is I've only created composite 4, so when I run this workload, it's definitely going to use composite 4 because composite 5 does not exist. It's going to be satisfied. But the question that was asked to me is, why isn't the optimizer recommending, using the missing index hint, that it could actually go and create composite 5? So that hint is not coming up here. Remember that missing index feature that we talked about, the SSMS missing index feature or the missing index DMVs. How many of you know about the missing index DMVs? Right? There are those DMVs which will get collated with all the missing indexes. It's actually the same code, both the SSMS and the missing index DMV. The point is, missing index DMV, remember, as the name suggests, it's only going to recommend you indexes when they do not exist. But because the optimizer has composite 4 for its use, it's not going to tell you that a better index could exist, right? If the index is not there at all, it would tell you to go and create indexes. But because composite 4 is already there, it's not going to tell you that a better index could exist. This is where your deep knowledge about the indexes on the optimizer will come into use. So you know that, and I will tell you why, composite 5 is actually a better choice over composite 4. And now we run this, and you can see composite 5 is being taken. So the question is, why composite 5 over composite 4? The short answer to this is, in a multi-column index, this is a multi-column index, right? In a multi-column index, the index can be used to seek on the second column if there is an equality predicate on the first column. That's the rule of the optimizer. A less known fact, a very less known fact about the optimizer and its choice of indexes. So the index, I repeat, the index can be used to seek on the second column if there is an equality predicate on the first column. Or to put it in other words, if suppose there were 3 columns, it can actually seek on the third column only if there are equality considerations on all the previous columns. That's the point. So if you look at the first example here, on first name equals to L and email promotion equals to L. We had like operator with first name, isn't it? Like L%. So we had the like operator. If we had equality operator with first name, then both composite 4 and composite 5 would be equivalent. Both composite 4 and composite 5 would be equivalent if first name had the like operator. So in the first example, first name and email promotion, I say true because this index is fully seekable. If you have both the columns using the equality operator, the optimizer can seek both on first name as well as email promotion. The order of columns are not important here because both of them have equality operator. In the second case, we say it's partially true. Oops, sorry. First name like L%. This is our example that we ran. The optimizer is actually able to seek on first name, but it is not able to seek on email promotion because first name does not use equality consideration. And just like in the previous example, I can actually hover onto the tooltip of the operator in the execution plan, and we can prove it using the residual predicate. Right? And the last one is definitely false, because if you have a predicate like first name like percentage L, which is definitely not seekable. You know, you say percentage, wildcard character there, percentage L, so you can't seek. Which means if you have an index on first name and email promotion and you give the third workload like this, it's only going to use the index for scanning purposes. It can't seek. So, you know, the multi-column index is slightly more trickier than a single column index. A single column index is relatively very straightforward. All the first 3 examples under true, first name like L%, email promotion equals to 1, contact ID less than 10,000. This is something which is known, very well known, that you can seek on all the 3 columns. So like operator L%, email promotion equals to 1 or less than 10,000, you can seek on these 3 columns. The other 3 under false, you can't seek on them, right? Which is I'm sure you have heard of these terms, which is called as sargable, right? It's not an English word, sargable, search argument able. The next 3 examples which are under false are non-sargable queries, which means you can't actually seek on them. Percentage L, you apply a function like a date function or an absolute function on the column on which you want to seek before the comparison. So you apply a function on the column before you compare with a predicate or a literal. So that's the second one. You can't seek, you can only scan. And the third one, you're computing on the column, contact ID plus 1. You're computing on the column before the comparison. So you can't seek on these 3 criteria, you can only search. So the single column index is relatively straightforward, but yes, multi-column index is where it gets tricky. So the short answer is yes, you can, the index can seek on the second column if there is an equality predicate on the first column. The long answer here is common guideline as it is. Most selective column should be the first column in your index key formation. All of you agree with me? Yeah, that's the common guideline. And if we really follow this common guideline, first name should be our first column. But as I said, this common guideline, I'm completely okay with this guideline or with this best practice. There's no dispute. But this should come with a rider. This should come with a caveat. The caveat is, my second bullet point there, most selective column should be the first column when all other column predicates use the equality operator. That should be the real guideline. If suppose all other predicates actually use the equality predicate, then you could have first column as the first column or email promotion as the second column. It wouldn't make any difference because you will be able to seek on both the columns. If you want to dive one step more deep into understanding why really does the optimizer behave this way. How many of you have actually worked with statistics, or you go and look into the statistics of the columns and the distribution of data? Have you ever, yes, great, that's great. Have you ever observed that histogram, histogram, which is the distribution of values in a column, histogram only exists for the first column? Have you ever noticed that? So if you have a multi-column index, histogram will only be there for the first column. And I won't go further deep into this. I'll leave it for you to really understand this. But the point that I'm trying to make here is, if I look into the statistics of composite 4, look at this. The histogram is only available, range high key, range rows. I won't go into the explanation of these as of now. That will deviate us. But the point is, histogram, the distribution of data in first name, it's only available for the first column, which is first name. But in case of composite 5, the distribution of data is available for email promotion. That's, again, only one column. So think about it. One of the columns in the statistics equal rows, it actually tells you the number of rows that are equal to the range high key, which means I have 11158 rows which is equal to 0, another number of rows which is equal to 1, and another number of rows which is equal to 2. So think about it. From the histogram, if the first column uses equality predicate, you can exactly find out the number of rows that are going to match the criteria of the first column. True? But in the previous example, if you take the example of first name like L, you can't find the exact number of rows that match L%. Because the histogram with this kind of structure can only give you an approximate values. When you have the exact values, which is the second case of email promotion, you can seek on email promotion, get the exact number of rows that match equal to 1, and then seek on first name. But you can't do that with the first index because it uses a like operator. Yes, sir. If you have more than 200, absolutely. If you have more than 200 distinct values, yes, a valid point out there. I haven't looked into that scenario, but we'll take it off. But a very valid point, because histogram can only have up to 200 steps in a write. Point well taken. So that's really going deep into understanding how the optimizer actually uses statistics to choose the right indexes given a set of choices. There's another interesting aspect. I have some time, so because I can't can't see take a tooltip on both composite 4 and composite 5, but just to make them to prove the point that in the case of first index composite 4, email promotion was actually becoming a residual predicate, right? Because it was seeking on first name, not on email promotion. You can see that here. So on the right-hand side is composite 5, and on the left-hand side is the tooltip of composite 4, which is seek. And you can see here in composite 5, which we use, you can see there is no email promotion here. There's no email promotion in this residual predicate because it goes into the seek predicate at the bottom there. But in composite 4, you can see that email promotion actually goes somewhere here into the residual predicate. I won't go into explaining every aspect of seek, start, prefix, end, etc. That requires a lot of time. But just to prove my point that you can see email promotion on the residual predicate on your composite 4 left side, but not on the right side, which just proves the point that you are able to seek on composite 5, both the columns, but not on the composite 4. There's another interesting aspect with this that I want to show you, and let me take both of them. It's just not about the efficiency of the execution plan in terms of performance. It is also about I/O. so the point here is, if I turn statistics, statistics IO, is my spelling wrong? Okay, statistics IO on, and I run both of them, one with the hint and the other one without the hint, so just to see both, and I look into this. Look at this. With composite 4, you have 6 logical reads, and with composite 5, you have 4 logical reads. That's another interesting aspect. So the performance of the execution plan is one part of the story, that you have a better execution plan with composite 5. Now when the query is actually executed, and the storage engine is fetching data from the disk, we have logical reads because the data is already in memory, otherwise it would have been physical reads. The story is when the data is being read from the disk, the storage engine is actually fetching 6 pages for composite 4 and 4 pages for composite 5. That's another interesting aspect, and that happens because of how the data is actually laid out. So I've put this as if time permits. So here you will see, because we have an index, so we have a root page, and the way how the data is laid down with this one, so you have the first name followed by email promotion. So just a pictorial, may not be very accurate, this diagram, but just a pictorial representation of composite 4 in the first case. So you have first name followed by email promotion, so how the data is being scattered. So given the predicate values, it lands up scanning the root page, the seeking on the root page and the data and the leaf level. So it actually scans 6 pages. It touches 6 pages. In the second case, the way the data is laid down, first with email promotion, it gets better organized for that given query. First, email promotion followed by first name. It touches the root page and seeks on 2 leaf levels. So the I/O is less, and which results in performance, right? So you have less I/O, you have better execution time for the query. So that's with the multi-column index. What about the database tuning advisor and the missing index feature? So if you are a senior DBA, the left one, you're going to be extremely angry on these tools, database tuning advisor and the missing index feature. If you're a junior DBA, you just started with SQL, have a little experience, you still are going to be a little upset. And if you're new to SQL Server, that's the best one. You're going to be like, what's happening? What's going on? Yeah, that's the third one. So I'm a SQL Server MVP for last 8 years, working with eDominer and people in India, back in India with these customers. The message that I'm trying to give you is not that these tools are bad or these tools should not be used. These tools are great. Believe me, these tools are very good. They're great. They work fantastic 90% of the times, right? But there are certain scenarios, certain cases, the ones that I kind of demoed today, in those scenarios, they kind of falter a bit because of the limitations of these tools, right? You may call them as imperfect. That's your choice. But for example, Database Tuning Advisor is an independent tool. It creates hypothetical indexes, use the statistics that are there, et cetera, to give you the recommendations. So the idea really here is these tools should be used, but please use them with your own judgment or your own consideration. Don't follow their recommendations blindly. That's the point that I'm trying to make. So back to the takeaways. So we had this missing index feature, when, why, and how. We have understood the when to use missing index feature, when not to, review them, et cetera, and that was and let me also tell you, the first example that I showed you on missing index feature, when you get one recommendation and then you get the second recommendation, right? That's not the behavior in SQL Server 2008 R2. That's a behavior we see with one of our customers in 2012. So I reproduced that in 2008 R2. It was not giving me the second index recommendation. So, this is like with changing product, with the changing code, how you kind of need to review such things. Because if you if your customer, for example, maybe is amateur and just goes on creating indexes the way the recommendations come in, it's going to lead to a disaster having so many indexes. The second one was your takeaway on left-based subset, and you saw that actually it sounds very easy on the putting down the order of columns in an index. It sounds easy, it's trivial, but it's really not the case. Sometimes it gets very tricky. The fourth one on the column order in a multi-column index, equality and inequality predicate. So that's really where the focus was with the third demo, and of course the database tuning advisor. In a nutshell, this session really talked about the optimizer's choice of index. But one last message that I have for you is there is absolutely no substitute to your deep knowledge about the optimizer and the indexes. Come what may, every commercial database product has some independent tools like these to give you recommendations, but your deep knowledge on the optimizer and the indexes is what is going to make all the difference. So there's no substitute to that. Summary and call to action. You can browse this recording once again to follow all that we did. The scripts and the presentation is going to be available on Channel Line, and I will also upload it on one of my websites where I blog, which is SQLServerGeeks.com. By any chance, how many of you have visited SQLServerGeeks.com? Oh, some of you. That's nice. So we started off this initiative some time back, and we blog out there. Try out these code snippets yourself. Download them, and they all run on AdventureWorks, etc., which is available on CodePlex. You can try them out. You can see the differences that I talked about, and the knowledge that you get from there. Try to review your indexing strategy in your environment. That would be the real goal of this session. All these little things that we talked about. Try out various combinations. I have my community cards here in case you want to collect one. I'll be glad. And I'll leave the stage for the next speaker. Thank you very much for coming to this session. It was a pleasure delivering it for you, and I hope it was worth your time, which is the most important thing for me. Please, please, please go and fill out the eval forms. Let me know where I can improve, and if you really enjoyed this session, would love to hear from you. Thank you very much. And my Twitter is _Bansal, in case you want to follow me.